All right, so in theory, I'm sharing my screen and it's recording. And if all goes well, you can now see a slideshow with a big slide that says polymers and it says thermoplastic and thermoset. Is that what you're seeing?
Yep.
Excellent. Yeah, let's hope it's actually recording. So, as I said, there are two types of polymer based on properties. Thermoplastics, those are the ones that have that state of plasticity, so you can melt and remold them multiple times. And a lot of the plastics that you think of that are used for like food containers are molded by blow molding. So you'll put a little bit of the kind of molten plastic into a mold, and then you'll blow air in, which will force that plastic out to the sides of the mold. And by controlling the air pressure, you can control the thickness of the plastic. And then the other type is thermosets. Those are cured somehow, and you can't return it to plasticity once you've cured it, so you can't melt thermoset polymers. So those are things like Formica tabletops, or like the Bakelite handles of pots that you use for heat resistance. And they're usually cured by like maybe UV light, or maybe sometimes they're cured by heat or an electron beam. There's various different ways that you can cure the polymer that can basically initiates, when we say cured, it initiates the polymerization reaction. And then there are so examples of those that you're familiar with. Most of the polymers you think of as plastic, PETE, that's polyethylene terephthalate. That is actually a condensation polymer. It's the only one of the numbered polymers. It's not an addition polymer, so not made from alkenes. That's made from ethylene glycol and terephthalic acid. The T stands for terephthalic acid, which is 1,4-benzene dicarboxylic acid, and the E and the second E stands for the ethylene glycol. High density polyethylene is 2, polystyrene is 6. So all of the recycling numbers except for PETE are also, in addition to being thermoplastics, they're addition polymers. And then thermosets, epoxies, adhesives, phenolic resins like Bakelite, coatings, they're often thermoset polymers. So they make a very hard coating that's chemical resistant and isn't subject to breakdown. And then based on structure, we talked about addition polymers. The monomer units for those are always alkenes. Often it's just a single monomer unit, but you can actually have copolymers where you have more than one monomer unit. And sometimes you can get those copolymers to be a nice repeating unit, and sometimes it's kind of randomly distributed. So you might have 5% 1,1-dichloroethene in 95% 1-chloroethene. And then condensation polymers, where usually more than one monomer unit. One of the reasons they're called condensation polymers, it's often water that's being eliminated, and so that condenses on the walls of the reaction vessel. And usually those step growth polymers or condensation polymers, you're making those from carboxylic acids and amines or alcohols. And if you make carboxylic acids plus alcohols, you get polyesters. And if you make carboxylic acids plus amines, you get polyamides. Nylon is a polyamide. And if you use a carbamate, you can get a polyurethane, which has a carbon oxygen double bond with nitrogen on one side and oxygen on the other. So we're not going to talk about those. You made one of those last year in general chemistry, because silly putty is a condensation polymer. You made that from dimethyl disilonol, so you had 2 OH groups and 2 methyl groups on a silicon, and then you eliminated water to make the SiO-Si bond. The GC stationary phase, the 5% diphenyl, 95% dimethyl polysiloxane, is a copolymer of diphenyl disilonol and dimethyl disilonol, but that's a condensation polymer. So as I said, all of the numbered polymers except PETE are addition polymers. Also superglue, Lucite, Orlon, which is used for carpets. Most rubbers, neoprene, which is actually very closely related to rubber, Teflon, those are all addition polymers. But polyesters, Dacron is a polyester, nylon is a polyamide, Kevlar is a polyamide, Lexan polycarbonate obviously is a polycarbonate that's got a carbon-oxygen double bond that has oxygen on both sides, as opposed to a polyurethane which has oxygen on one side and nitrogen on the other, and then the silicones, which have that repeated SiO with various things attached to the silicone. Those are all condensation polymers. And we'll talk about them a little bit next semester when we're talking about amides and esters anyway. In principle, and the reason you'll see some things that are pretty obvious to you, like an alkene is a carbon-carbon double bond, is this PowerPoint was originally designed for environmental chemistry, and they didn't know anything about alkenes. Right, so in principle, thermoplastic polymers can be recycled. You can melt, you can remold, you can melt, remold, but the high temperatures and the exposure to the environment often leads to oxidative degradation, so your monomer unit, you can't reform the monomer, right? No one's figured out a way of unzipping a polymer to regenerate the monomer unit yet. There's a lot of money to be made if you can figure that out. So the polymer degrades, and usually it degrades by oxidation, and that gradually reduces the melting temperature. And it also leads to discoloration. So if you want a nice, clear, transparent pop bottle, after a little degradation, it's going to start turning yellow. And you probably don't want to buy your beverages in a urine-colored bottle, even though the contents would be the same. It would look dirty. So in many cases, you'll reuse them or downcycle them. So you're probably familiar with the fact that pop bottles that are made of polyethylene terephthalate can be ground up and spun into fibers, which can then be used to make clothing. So if you own a jacket that's a polymer, it's probably made from recycled pop bottles. So styrofoam cups are often made to make synthetic lumber. So you buy plastic decking or plastic fence posts, which are great because they don't rot, but not so great when a hurricane comes along and takes the whole thing and takes it out to sea, and it ends up in the Pacific garbage bag. Thermoset polymers are inherently not recyclable. The most common kind of reuse for a thermoset polymer is to grind it up into a sand and use it for like road bedding. And that's actually one of the main uses for recycled glass as well. Since you can't get consumers to actually separate their brown glass and their green glass and their colorless glass, and a mixture of colored glasses is useless, because then when you melt them and make new glass, it turns out it's kind of a non-uniform gray color. Generally, glass is just ground up and used as an alternative for sand when they're putting roads together. And there's not that much of a market for recycled glass either. If we were capable of separating them by color, there'd be more of a market. I'm going to skip that, because that's, if you want to know about recycling, you can go there. So almost all the raw materials for synthetic polymers come from petroleum, and it's actually a byproduct. Ethylene, from which polyethylene is made, used to just be burned off during petroleum refining. It was a useless byproduct. They just sent it up and they'd have this flame, this plume. If you've ever driven by the petrochemical plants down in Louisiana and Mississippi, Texas, you'll see that there's often a constantly burning flame somewhere above the chemical plant, and that's just burning off the things that they can't figure out what to use for when they're cracking petroleum to make the different cuts, when they're doing that pyrolysis process that we talked about in chapter 3. So generic addition polymers, there's an R group, there's something, right? That R could be hydrogen, but it could be lots and lots of other things, and they're attached head to tail, and you'll see down below I showed the repeating unit, which is CH2CHR and then CH2CHR. So that's a head to tail polymer. The carbon that's attached to the R group is going to stabilize either an anion or a cation or a radical that causes it to add in that head to tail fashion. Not all polymers are head to tail polymers like that, especially some of the condensation polymers, the step growth polymers, might have some head-to-head linkages in there, so you don't have a completely uniform repeating unit like you do with the addition polymers. Here's just a list of properties that influence function. Melting temperature is obviously one that's very important. High melting temperature is going to be required if you are using your polymer somewhere where it's subject to heat. Density is important. One of the reasons why polypropylene containers, which is number 5, have been gradually replacing high-density polyethylene containers, which is number 2. If you follow the little numbers, you'll notice that more and more containers seem to be made of 5 rather than 2. Polypropylene is slightly less dense than polyethylene. And if you're shipping billions of items, the slightly lower density means slightly lower weight for your containers, and that means less fuel to ship them by truck or by plane. Degree of crystallinity, that affects to some extent the clarity. The more crystalline polymers are usually clearer. Flexibility, elasticity, right? Rubbers are elastic, most polymers are not elastic. Shear strength, high density polyethylene, very long chain linear polyethylene is really strong. You can use that, just a really thin fiber like that. It's as strong or stronger than spider silk. Impact resistance, right? That's important in things like Kevlar or Lucite or Lexan, like the things that diving helmets are made of, or motorcycle helmets. Solvent resistance, right? If something's going to be used in an environment that has a lot of organic solvents, you want it to not dissolve. You'll notice if you've ever tried to clean your goggles with acetone that Lucite that the goggle glass is made of is not solvent resistant to acetone, and you won't be using the goggles again if you clean them with acetone. So the properties depend on the structure, right? The different R groups going to yield different properties. They depend heavily on the length of the chain, the average chain length. The longer chains are more rigid, they melt at higher temperatures, and as I said, the properties of the polymers are most dependent on the length of the longest chain. So even though a 99% yield reaction is going to have an average chain length of about 100 units, some of those might be very long, especially with the metal catalyzed polymerization, and those very long chains are going to have a disproportionate impact on the properties. Branching, right, we talked about that a little bit, and then tacticity. If you have a single R group, you generate a chiral center when you add that, right? Because you've got the two ends of the carbon chain, you've got hydrogen, you've got the R group. And they can then be randomly distributed, which is atactic, or they can all be on the same side. That's an isotactic polymer, so like all of the chiral centers would all be R, for example, or all S. And then syndiotactic is when the R groups alternate sides, where you might have an R stereocenter, and then the next one's an S, and then an R, and then an S. And that tacticity is going to determine the properties. And we'll see that some polymers, it's the isotactic form that's useful, and some polymers, it's the syndiotactic form that's useful. So probably the simplest polymer is polyethylene, right, where the R group is hydrogen. Simplest alkene, HDPE, a very linear, no branching there, just CH2, CH2 over and over again. So the repeating unit here is boxed. It's the two CH2s adjacent to each other. It's not just a single CH2 for the repeating unit, because remember that the monomer units have to be an alkene, right? So you have to have a minimum of a 2-carbon repeating unit in order to have an addition polymer. Ziegler-Natta catalyst, that's titanium tetrachloride and triethyl aluminum. That's the, I think I said titanium tetraisopropoxide. You can use titanium tetrachloride as well. It's just something that's going to leave from the titanium. Drink bottles, food containers, plastic wrap, you've seen high-density polyethylene, it's everywhere. Low-density polyethylene is the same monomer but radical polymerization, so you get that branching because you start getting those hydrogen abstraction reactions, and then you have radicals in more than one place on the chain, and they can elongate from both of those new radicals. Plastic bags are low-density polyethylene, so all of your shopping bags that you get. And then often the lids to a food container are low-density polyethylene, whereas the container itself is high-density polyethylene, because you want more flexibility in the lid since you're taking that on and off. Although now you'll see that a lot of lids to food containers are in fact polypropylene, which is number 5. So LDPE I said is 4, right? HDPE is 2. You can't recycle them together, because if you introduce some of the 4, the low-density polyethylene, into your high-density polyethylene, now you've got a polymer which doesn't have those desired rigidity properties. So that's why in Ohio anyway, only high-density polyethylene and polyethylene terephthalate, which is 1, only 1s and 2s are collected. And 4s you can recycle plastic bags separately, if you take them back to the supermarket that you got them from. The reason why you can actually recycle 1s and 2s together is because the difference in density. Because the polyethylene terephthalate has a bunch of oxygen in it, and oxygen is a heavier element, it's more dense than water. Whereas the high density polyethylene, which is just CH2CH2, that's less dense than water. So you can grind those up and put them in water, and the polyethylene terephthalate, the number 1 plastics, will sink, and the number 2 high density polyethylene will float. And so you can float your one polymer off, and you can get the other polymer to sink, and that way you don't have to rely on people to separate the 1s and 2s. You can mix those together and then separate them just by whether they float or sink in water. Polypropylene has 1 methyl group, so it's propene as opposed to ethene. You can make isotactic or syndiotactic versions of polypropylene, but the commercially useful one is the isotactic, and that's made by Ziegler-Natta polymerization. By using that metal surface to bind those units together, you can make sure that the methyl groups are always on the same side, so you have the same stereocenter all the way across. You'll notice in this one I bracketed every other repeating unit. Right, so the repeating unit is CH2, CH, CH3. It's the lowest density polymer. Margarine tubs, upholstery, indoor-outdoor carpeting. It's used for all kinds of things. Polypropylene is one of the original synthetic sources for long underwear. The disadvantage, of course, is polypropylene long underwear. If you've ever put them in a gas-powered dryer that's too hot, they'll melt in the dryer and stick to everything. The British Navy at one point replaced the long underwear for their sailors from wool to polypropylene because it has the advantage of being lighter. But the problem is when the ship catches fire, polypropylene long underwear will actually melt to your body, whereas wool long underwear won't. So they actually, after a couple of kind of boats caught fire during the Falkland Islands War, they went back to wool instead of polypropylene. They both have the benefit of staying warm when they're wet. Polyvinyl chloride, PVC, right? That one is a major target right now. The monomer unit for this is incredibly toxic. So people that worked in plants that made polyvinyl chloride, particularly in Italy, had a very high-profile lawsuit where they weren't told of the dangers of the vinyl chloride, and there was a lot of long-term illness and injury as a result of exposure. The polymer is actually pretty safe, but the monomer unit is often trapped within the polymer. Generally, it's the atactic form of polyvinyl chloride that's used. It's made by radical polymerization, so you have no control over the tacticity when you're doing a radical polymerization. And the polyvinyl chloride plastics often have a lot of plasticizer in them. If you followed kind of environmental causes about plastics, you're probably familiar with the idea that phthalates are something that you don't want. And phthalates are often used to improve the flexibility. So if you have a polyvinyl chloride raincoat, for example, it might only be 60 or 65% polyvinyl chloride, and the other 40% are additives that are added to improve flexibility. And those are often phthalates, which are estrogen-like substances that cause hermaphroditism in fish and things like that. One of the main uses for polyvinyl chloride is pipe for plumbing, to replace, especially in drains, to replace the metal pipe that has a tendency to rust. So if you go into Home Depot or Lowe's, the white plastic pipe is polyvinyl chloride. That's PVC. It's used for furniture, kind of synthetic leather furniture. It's used for vinyl siding for houses, floor tiles. Floor tiles used to be asbestos-based, but asbestos is now kind of out. And then anything that's really flexible, squeeze bottles, garden hoses. Polyvinyl chloride is very important in the medical industry because polyvinyl chloride bags have low porosity to oxygen. They're very useful for blood, for when you're giving transfusions. They kind of revolutionized battlefield medicine because it used to be that the blood for soldiers that are injured in the field of war were glass, and you had to hold that glass bottle up, and the blood would then flow by gravity, and the person holding the bottle up would be exposed to enemy fire. So switching those glass bottles for blood transfusion to PVC allowed the person to lay low and just squeeze the bottle to push the blood into the person that they were trying to do a transfusion. It's self-extinguishing to fire, which is kind of nice. PVC is one of the few plastics that's not flammable, but of course when it burns it releases chlorine radical into the atmosphere, which is bad for the environment. So it's the environmentally unfriendly plastic because of that chlorine. Polystyrene has a phenyl group. In this case it's the syntactic form where the benzene ring alternates being up and being back. Has a very high melting temperature, about 270 degrees, versus the isotactic and atactic. Drink cups, food packaging, egg cartons, lots of food-based applications for polystyrene. And it's also a component of many copolymers, and one of which we'll talk about. If you go into Home Depot and you see that some of the pipe is white, that's polyvinyl chloride, but some of the pipe is black, and the black is a copolymer of acrylonitrile, polystyrene, and butadiene, ABS plastic, acrylonitrile, butadiene, styrene. And we'll see that right at the end. So all of the ones we talked about so far just have one R group. Right? It's a CH2 and then a CHR. And the R group varies. It could be hydrogen, it can be methyl, it can be chlorine, it can be the benzene ring. Polyvinyl acetate. Right? It has that acetate group attached. It's the latex in latex paints, and it's used in chewing gum and as a coating for safety glass. And it's related to polyvinyl alcohol, right? Polyvinyl alcohol is an enol, though, so you can't actually make polyvinyl alcohol from hydroxyethene, because hydroxyethene would quickly rearrange to acetaldehyde. So what you do is you make polyvinyl acetate and then do a cleavage reaction where you would hydrolyze this with base, right? Push a pair of electrons out onto this oxygen and then come out and boot it out. Once it's made into the polymer, then the OH group is stable because it's now attached to an sp3 hybridized carbon. So you'll often see a mixture of polyvinyl alcohol and polyvinyl acetate in paint. And there's more information. Orlon or polyacrylonitrile, right? It's also called acrylan. Acrylan and Orlon are just two different trade names from different companies for polyacrylonitrile. Fake fur and synthetic fabrics, especially carpet. If you buy plastic carpet, it's often Orlon as opposed to wool carpet. What kind of polymerization process would you think you would use for making polyacrylonitrile or Orlon? What would be the logical choice? You still awake? Maybe.
We're still here.
Yep, so you got four choices. You have a 25% chance of randomly guessing correctly what type of polymerization for Orlon. Is the C triple bond N group electron withdrawing or electron donating?
Would it be anion catalyzed?
Yes, because the nitrogen is more electronegative, right? Which means you actually have a resonance structure for that molecule where there would be a positive charge on the carbon and a negative charge on the nitrogen and just a carbon-nitrogen double bond. That positively charged carbon is in a what we call an allylic position adjacent to the pi bond, which means that you can also draw a resonance structure that has a positive charge on the CH2 group, right? And the negative charge out on the nitrogen. So that positively charged or positively polarized CH2 group can get attacked by an adjacent pi bond from another molecule, and you can gradually build that up. So electron withdrawing group, anionic polymerization. Polyisobutylene, which is the one I was first talking about when we were doing the initial acid catalyzed polymerization, is a disubstitute alkene. So now we don't have to worry about tacticity, which is kind of nice since we've got a symmetrical molecule, and that's called Elastol. It's used for bicycle tires and inner tubes and copolymers. And it's also used for oil spill cleanup. You can take a net made of polyisobutylene and spread it out over an oil spill on a body of water, and it'll suck up that used oil, and then when you pull the net back in, you can actually kind of wring it out and the oil will come off and you can reuse those nets. Saran, which is polyvinylidene dichloride, used to be the major substance that you would use for food wrap. It's actually a copolymer of the vinyl chloride and vinylidene chloride, which has the 2 chlorines on it. Really low porosity, which is nice. It kept food fresh for a long time. Clings really nicely, but because of the chlorine containing, most food wrap that you buy now, even if it's the Saran brand, isn't polyvinylidene dichloride anymore. It's mostly high density polyethylene. High density polyethylene is not as good as a food wrap as Saran, but environmentally it's much more friendly, so the Saran has been gradually phased out. It's one of the first polymers. I think DuPont is the company that developed Saran. Lucite is polymethyl methacrylate, so you've got a carbon-oxygen double bond, you've got this ester group attached, right? And that same ester group is what's attached on superglue. The only difference is we have a CH3 group here instead of a nitrile. That's plexiglass, impact-resistant paneling, lighting fixtures, skylights. It's basically a glass substitute. Contact lenses are made of polymethyl methacrylate. And again, anionic polymerization because we've got an electron withdrawing carbon-oxygen double bond here. And then superglue is polycyanoacrylate. You'll notice a very similar structure, right? Superglue and lucite differ only here, right? A methyl group for lucite, a cyano group for superglue. This polymerizes very rapidly, so as soon as you open that bottle and put that on there and there's a little bit of hydroxide ion present, it'll stick your fingers together almost instantly. And then it's not so easy to dissolve. It's got good chemical resistance as well. Teflon is a tetra-substituted alkene. It's tetrafluoroethylene, and you'll probably quite familiar with that. Used in nonstick cookware, can liners, cable insulation. It's the one side of the Teflon silicone septa that we use for the GC mass spec vials or to store our compounds. It was discovered initially by accident. Tetrafluoroethylene is a gas which was kept in large metal gas cylinders, and the discovery of Teflon resulted when a gas cylinder wasn't liberating gas anymore. They opened the container, no gas came out, but the cylinder was heavy, so it didn't have a mass consistent with the gas having been used up. So if you were confronted with that situation and you had a compressed gas cylinder that used to contain tetrafluoroethylene and it seems like it's still full because it's heavy, but you can't get the gas to come out when you open up the regulator, what would you do? What would be the first thing that would occur to you? Probably not what these people decided to do, which is take a bandsaw and cut the tank in half. So when they did, and they took the bandsaw and cut the tank in half, what they discovered was that the cylinder was in fact full, not of gas, but of a kind of slippery white waxy substance. And that slippery white waxy substance was the polymer. Somehow the gas got contaminated, something got in there that initiated a polymerization process, and so they got Teflon. It was kept secret. The military thought that there were lots of potential military applications, so it took a long time before the structure and the properties of Teflon were actually released to the public. It's really inert, so it can be used in the body. Artificial heart valves and joints will have Teflon on them. It has a very high softening point, thermally stable, and it's just repeating CF2 units. So the repeating unit here is a pair of adjacent CF2s. It's basically high-density polyethylene where all of the hydrogens have been replaced by fluorine, and commercially it's a very important polymer. Polybutadiene is rubber. Someone said that rubber was one of the first things that came to mind when you talked about polymers. There's 2 double bonds in polybutadiene, so it can actually be polymerized where this is just the R group, the stuff that's in orange there, and you have a vinyl group hanging off the end, so CH2, CH vinyl, CH2, CH vinyl. But because you've got a resonance structure for this that has a positive charge on one end and the double bond in the middle and a negative charge on the other end, it can also polymerize in a 1,4 fashion, so your repeating unit actually has 4 carbons in it instead of 2. So CH2 and then the CH-CH double bond and then a CH2. It's always the cis double bond in Buna rubber, and so you get a repeating unit. It's useful because there's a double bond in there, so the polymer is still reactive. You can actually cross-link it because there's a double bond in here, and you can get that double bond to add to a double bond in another chain, and you can generate a 2-dimensional structure as opposed to a 1-dimensional structure, which will then be flexible for pulling kind of end on end as well as pulling in the adjacent, right? Normally when you have something like high density polyethylene, it's really strong for pulling in one direction because you're pulling on the ends of the polymer chain, but it's really weak on a shear stress for pulling in the other direction because there's nothing that's holding those chains together. Cross-linked rubber. It's often cross-linked by just heating in the presence of elemental sulfur, and what you'll end up with is disulfide bonds where you have the double bond reacting with sulfur, and you have a carbon here and then a sulfur and then a carbon of another chain on the other side, and that's called vulcanization. Heating rubber in the presence of sulfur is vulcanization. Vulcan, the Norse god of fire, and that generates the rubber that you actually see used in tires. And then the last thing, I think this is the last slide, we talked about copolymers. ABS copolymer, right? It's acrylonitrile. If you polymerize that by yourself, you get Orlon, which you can use for making carpet. If you polymerize kind of butadiene by itself, you get Buna rubber, which can be used in tires and things like that. If you polymerize the styrene by itself, you get polystyrene, which is used in food containers. But if you do a random copolymer of a certain percentage of acrylonitrile, a certain percentage of butadiene, and a certain percentage of styrene, that's a very hard plastic. I didn't mean to exit. And you can use that for bumpers and crash helmets, telephones, luggage. ABS copolymer is used for all kinds of things because of its great durability and rigidity. And it doesn't have the environmental concerns that PVC pipe has. Why not? What does PVC pipe have in it that's not so good for the environment? Chlorine, right? So no chlorine, ABS pipe. It does have this cyanide group in there. So acrylonitrile is not the safest substance in the world, but once it's polymerized, that nitrile group's not going anywhere. Right? And that's actually true of a lot of plastics, that the monomers are toxic, but the polymer itself is non-toxic. So a very important process in plastics formulation is making sure that there's no residual monomer left in the plastic before you're making containers with it. That's particularly important for food containers, right? You don't want to be eating small quantities of monomer. And you may or may not have read or heard about the controversy with bisphenol A or BPA. Are you familiar with everybody trying to claim that their polycarbonate water bottles are BPA free? Right? Bisphenol A is the monomer. It's a thermoset polymer. But the presence of small quantities of monomer bisphenol A in your resulting plastic can cause very bad effects, especially on developing fetuses and children because of its estrogenic properties. So that's it. Those slides are actually available on Blackboard already.